Hello everybody, Mr. Hasty here. Today we're going to be talking about the continuation of section 8.2, which is on the concept of what's called O notation. So we talk about how things have relative growth rates, and if the relative growth rate of f of x is less than g of x, we will say something along the lines of f is little o of g. That means that f is of a smaller order than g. So let's get a formal definition for that. So let f and g be positive for large x's. So that whole statement just says that we're dealing with positive functions once x gets to be pretty high. Then f is smaller order than g if the following holds. The limit as x goes to infinity of f of x over g of x equals 0. So yesterday we talked about relative growth rates, and we talked about how if g is growing faster than f, in this situation the limit as x goes to infinity would be 0. So this is also equivalent to saying the limit as x goes to infinity of g of x over f of x is infinity. So if you reversed them, it could also be true for if it equaled infinity. Now we have a specific notation. If this is true, we write f equals little o of g. And the way this is said is just as I said it, f equals little o of g. So when we say that f equals little o over g, we're pretty much just saying f is slower than g. So let's look at a couple examples of that. So example 1, let's do these kind of as proofs. We're going to prove that the following statements are true. Let's prove that x squared is little o of e to the x. So to do that, we just simply set up, if we're assuming that we're assuming that this is the larger, faster growing function. So the one inside is faster growing. We want that on bottom. So we're going to do the limit as x goes to infinity of x squared over e to the x. And we need to show this equals 0. Well, currently it would be infinity over infinity, so this is where L'Hopital's rule comes in. Limit as x goes to infinity of 2x over e to the x. Derivative of e to the x is e to the x. Again, infinity over infinity. We apply L'Hopital a second time. We get 2 over e to the x. If we plug infinity here, we get 2 over infinity, which would be 0. So that's kind of like showing the result shows it. You could do a proof indicator there. It's not necessary. So let's compare another one. Let's do x is little o of x cubed plus 1. On this one, we're not going to have to apply a L'Hopital's rule. You could apply L'Hopital's rule, but you don't need to. In this one, I'm going to go back to a trick that we learned a long time ago, and that is if we have a rational function, which means polynomial on top, polynomial on bottom, then there's a trick that says if the top exponent degree is smaller than the bottom, then that's automatically going to go to 0. Now, if you wanted to L'Hopital it, and that would be done using that rule, if you wanted to L'Hopital it, it would quickly go to being 1 over 3x squared. And you could easily see that it's going to be 1 over infinity, which is also 0. So either one of those is sufficient to prove this is true. So there's another form called big O notation. So let's get a definition of that. Let f and g be positive for large x's. And that again is just handling the fact that for like small numbers around 0 or negative numbers, they could be doing who knows what. But once x gets sufficiently large, they are positive. And that's important. Then f is, and this is tricky wording, at most the order of g. And what we mean by that is at most means it grows as fast or it grows slower. Those are the options. If the limit as x goes to infinity of f of x over g of x is less than or equal to m, where m can be any integer. I should say positive integer. And we would write that as f is little o of g. Now I will make ridiculously sized o's because it's really important to make sure that we can just tell the distinction between little o and big O notation. So usually my big O's will be, my little O's will be little tiny, and my big O's will be really, really big. That way there's never any confusion as to which one I'm talking about. So let's see a couple examples of that. So example 3, we're going to show that x squared plus cosine x is big O of x squared. So the way this gets set up is the one on this side always ends up on bottom. And you can do this in reverse orders. The important to keep that in mind, what I mean by that is our setup according to the definition is going to be the limit as x goes to infinity of x squared plus cosine x over x squared. Now you could flip this and do it that way. There is a way to do that, but it's almost always easier if you put this one on bottom. So this one doesn't require L'Hopital's rule. It could be done with L'Hopital's rule. I'm just going to do some algebraic simplifications. I'm going to split the fraction on top into x squared over x squared plus cosine x over x squared. And if we think about that, that's going to be the limit as x goes to infinity of 1 plus cosine over x squared. So cosine x over x squared is going to get really, really, really big on bottom, but cosine's trapped between negative 1 and 1. So this is going to zero out. So this is going to equal 1, which is less than or equal to 1. As long as it's less than or equal to some positive integer, then we have shown that x squared plus cosine x is big O of x squared. So let's look at one more here. We're going to do something similar to a problem we've done in the past. So let's show that the square root of x squared plus 2 is big O of x. So when we do this, we're going to take the limit as x goes to infinity of root x squared plus 2 over x. And we're going to use a trick that we learned yesterday, which is to turn an x into the square root of x squared. And we can put it all under the same root now. And we can split the fraction and do some simplifications. 1 plus 2 over x squared. Now if we plug infinity in, we'll get 1 plus 0, the square root of that's just 1. And again, no L'Hopital's rule required here, we can just do it that way. So that is big O and little o notation. Kind of a shorter section there. And we'll be continuing on to 8.3, and we're only going to do a partial of that section, just the real basic version of it. All right, guys, talk to you later.